So hopefully everybody can see this. Can you see my screen or no?
Yes. Yes, we can see.
Yes.
Okay.
Yes.
Well, first, good afternoon, everyone. Thank you very much for CASPA inviting AAC and myself to share a few words on how we see integration technology. Actually, we fully align with Dr. Ryan's vision that data is transforming the industry and there's tremendous opportunity in the semiconductor space. And so one of the things, let me see if I can. One of the things that we all know is change is constant. 2020 has taught us tremendously about adapting and moving from what we used to know to what we need to be in this era of pandemic. And the same can be said about semiconductor. Semiconductor has moved tremendously, as like Dr. Ryan has indicated. You know, we went from mainframe to mini computer to PCs to mobile space. And all those things have transformed semiconductor and move us along from one step and one stage to another. So data is changing everything. So we agree that data is making semiconductor industry the next growth engine. And then if you look at less than 20 years ago, majority of the most valuable company are oil companies. Top 5 of this top 10 company listed are oil company. And you fast forward to today, you notice 7 out of 10 are all in the information business. They are in the data business. And then who drive semiconductor or leverage semiconductor to make their business possible. So let me try to. So that caused a significant growth in data. So the global data has increased dramatically from less than 20 years ago by 30 times, from 1 zettabyte to 33 zettabyte. But in less than 5 years, you will another go into 5x, so 175 zettabyte. So if what Dr. Ryan is saying is absolutely true, that if data is new oil, then we should look at how oil make money. So the monetization of oil as we see it is you explore and drilling, and then you refine it, and you monetize it through processing of various chemical fuels, different type of waxes and petroleum product that we use on a daily basis. And it's because of this process that oil company are becoming, or did become, the most profitable and most valuable company in the world. So then if data is the new oil, then how do we monetize data? As Dr. Ryan said before, that we are collecting the data, and those are the companies today are leading in collection of data. We're processing the data, and then that is through various communication, and then we monetize the data. So all the apps and social and all analytics, all the e-commerce, and all the hosting that is most profitable company in the world today are basically monetizing all the data that we collect and we process and we transmit. And then the people that can create this full ecosystem, such as Amazon, Apple, Alibaba, or Google, are the one that's leading in this data, super race. So this has driven us to the next growth in semiconductors. Semiconductor, if you look at how it has grown from 2014 to today, is majorly driven by mobile smartphones. And then recently, he kind of take a pause in a few years back, but then recently he has restarted again in terms of 5G, autonomous driving, AI, MI, and this is the data that is giving us the opportunity to resume the growth for overall semiconductor industry. So one of the segments that I want to kind of go through a few segments of how this thing has changed our life. If you look at the AI and machine learning accelerator market, you have seen that it touches everything that we do today in a society, whether it's in finance, whether it's in healthcare, whether it's in retails. And those are the things that are providing the driver or the growth engine for the semiconductor that we are using and that we'll be using in the future. So another thing that is giving us that additional opportunity is the advent of 5G. If you look at this, this chart, this 5G impact is not only creating communication expansion between human to human, it's actually giving us all the way to machine. So the idea of fully autonomous driving with cloud oversight become possible with the latency that 5G is providing, and ability for us to not only do the virtual reality or augmented reality through the high bandwidth that the 5G provide, but also the mass scale communication that can commit smart cities, smart homes, whether we can monitor healthcare, to be able to take care of the elderly, and all the way to the safety where everything are connected potentially to help us in the everyday life. So those are two key industries or segments that are driving the future of semiconductor today. So what does that say for integration opportunity? So when we look at semiconductor, we look at how Moore's law has changed and how that translates to applications. So when we look at IoT all the way to data centers, we look at all these different chips or sensors or modules that allow us to create this ecosystem that allow us to connect data from the very edge of communication all the way to processing the data and monetizing it and returning intelligent answer back to the users. And whether it's through the sensor that collect data, the connectivity that allow the sensor to communicate to the next step in the communication chain, to the 5G array antenna in overall infrastructure, to the silicon photonic that connect between the various server blades, to the final data centers that hopefully one day we can do the full homomorphic encryption solution that Dr. Ryan spoke of earlier. So those are the integration opportunity that we see that we will talk a little bit more in terms of how we're going to bridge those technology gap to provide these integrations. So one of the things that we see today is as semiconductor continue to advance, going from 5 nanometer down to 3 nanometer down to 2 nanometers, the ability for the PCB to connect to the outside world has not able to advance quite as fast. So if you look at the tightest geometry that the PCB today can provide, is probably around 5 microns, and maybe going down to 2. But microns and nanometers are significantly gaps. So how do we connect a 2 nanometer chips all the way up to a 5 micron line space PCB board? And those are the challenges that we think that the packaging are able to provide today. And if you look at the right chart, the die size continue to increase because of all the AI and machine learning requirements. So people are looking for more and more core in their processor or the GPUs or the neural engine. And then the costs continue to go up. So with those two drivers not in the semiconductor company's interest, then some of the idea of chiplets and to break up the die, then that create new challenges for packaging. And this is where we believe the opportunity resides. So one of the things that we see is the chip and system are converging. So if you look at all the packaging solution that has been offered throughout the history of semiconductor packaging, we are working towards SiP. And if you look at the system, as the system continues to shrink and increase complexity, we actually are creating opportunity for these two to converge, where we can create this heterogeneous integration that allow us to put the chips into a system and put completely different type of chips, whether it's analog, mixed signal, digital, or even sensor, all on the same platform for this overall integration convergence that we see today. So one of the things that we see in terms of the high performance computing or artificial intelligence packaging is the silicon integration. There's three aspects to the overall technology driver. Today, we're just really going to talk about silicon integration. Obviously, there's optical integration for silicon photonics or onboard optical solutions, and there's power integration, whether to drive the certain power for the high performance computing. But the die partition to improve the yields, the ability to integrate the high bandwidth memory, and the ability to reuse various IP and reduce the power is a key for silicon integration. And one of the solutions that we're able to provide is look at this overall computing platform. So we are looking at, if you look at the main chip on, maybe I can see this, main chip on this main silicon board, that could be a chiplet, could be a one monolithic flip chip parts. We are able to put memory on top of it. We're able to put various optical chiplet to communicate optical to the outside world. We are putting into very large packages. Now is basically 10 centimeter by 10 centimeters. So really are the key challenges for overall integration in terms of putting various different type of silicon in terms of heterogeneous integrations, able to put the power management module on top of, or actually on this particular case on the bottom of the packages, but to integrate all of them in a single package solution for the next high performance computing or next GPU applications. So those are the opportunity that we see in terms of creating this fully integrated solution for the new semiconductor space. So this can kind of give you kind of few options what we see today. So from the left to right, it's basically in terms of complexity, from standard flip chip, multi-chip modules to create a fan-out RDL on top of the chip, to create bridges between two chiplets, to create 2.5D through silicon via, basically with a silicon interposer, to full 3D construction. So in terms of all these integration solution that's available in the semiconductor packaging space, basically give the designer the option to create the most efficient way of creating this high density integrated packaging. Now, another thing that we see when we talked about earlier is the overall 5G. The 5G give us significant SiP or silicon in package growth. The reason is really about antenna. With 5G, especially with millimeter wave, whether it's 39, 60 gigahertz or 28 gigahertz today, if you look at the cell phone today, even before 5G, we're looking at almost 12 antenna in a cell phone. You need one for Wi-Fi, one for Bluetooth, one for GPS, and maybe 4 to 6 of them for LTE frequencies. And then on top of that, we have to put 3 to 4 additional 5G antenna. So those are the opportunity for us to then integrate those antenna into the package itself. Because the phone cannot get any bigger. Everybody wants thinner phones and they want more functions. So for us to do all these solutions into your handheld solutions, you need to reduce the overall form factor. And this is one of the ways we are thinking about doing it, right? Whether you through hybrid substrate or even do a fan out, basically RDL on top of the chip to create this antenna solution. And there's various shielding that we can provide to allow us to shield from one set of frequency to another, so we don't have too much interference. So one of the things that we are showing to is this toolbox that we could do. Whether it's a shielding I just spoke of earlier, to various interconnect, to create various complex antenna patterns, whether it is on the package or part of the substrate as a solution, whether it's overmolded, whether we can do passive directly onto the package itself. So there is tremendous amount of toolbox to allow creative designers to create the next SIP to a specific solution, whether it is very much on edge, all the way to the high density solution that could be sit on the server itself. So the toolbox to us and is quite extensive, and we continue to develop new toolbox to enable more creativity for the next generation SIP modules. So this kind of show you the roadmap that we see in terms of SIP. Back in 2016, it's basically overCAN, SMT, some passive, some packaging, some IC, and then we have very much in terms of trying to create shielding. We can now do antenna with selective shielding to create various different frequency within the same modules. We can do all the way to 3D SIP if necessary. We can do double-sided molding, so we can put IC on top and the bottom of the PC board to maximize density. And we can try to make those double-sided without frame to make it thin for the latest mobile or wearable solutions. And we even can put the chips inside the substrates to create an embedded solution that can create even more miniaturization. So the idea for us is really allow the designer today to try to put the various ASIC and various IC into this heterogeneous integration packaging that allow them to create the next revolutionary system in a package or system in the modules. Now this kind of aside, so the AAC has been doing this for past 10 years. We are basically able to integrate the OSAT that we do today with one of our sister company, USI in EMS, to create overall system module integrators. And this create the important bridge between the fab all the way to the system. And then this allows us to create the maximum flexibility and the maximum integration for the next semiconductor revolution. So that's it. Thank you.